So this video extends the idea of congruent figures into what we call similar figures. Now, going back to what we have talked about with congruent figures, we've seen congruent figures in a number of different contexts, and the way that we have talked about congruent figures is that they are identical in every way. Their corresponding angles have the same measure, and their corresponding sides have the same length. That is, every component of one figure that is congruent to another is congruent to the corresponding part of the other one. And if we go back to these diagrams of congruent figures, we can basically just think of it as a copy-paste. The triangle here in the upper left is congruent to the triangle in the bottom right because all of its sides are congruent to another, all of its angles are congruent to the other. Same thing is true with the trapezoid that I'll just leave overlapping there. Now, when we talk about similar figures, those relationships are slightly different. We can still think of it as one figure being a copy of sorts of another figure, but their sizes don't necessarily have to be the same. One triangle could be smaller than another triangle and still be similar as long as particular relationships are maintained. Similarly, we could have one trapezoid be similar to another trapezoid even though it is bigger than the other, and perhaps can fit around it like that. Those two trapezoids are similar, and those two triangles are similar, because in order for two figures to be similar, their corresponding angles must be congruent, and their corresponding sides must be proportional. Pause the video, write down this definition of similar figures, and then unpause when you are ready to move on. The first thing that we're going to do with similar figures is practice naming them. The same way that congruent figures need to be named in a particular way, similar figures need to be named in that same sort of strategy, which is as soon as you start with one congruent part of a similar figure, that is naming it according to one of its sides, the other figure must be named in the same relative order around the shape. So ABCDE is similar in this case to pentagon VWXYZ. And if we were going to name them, we can start with any vertex in ABCDE, and as long as we start with the same vertex in VWXYZ and move in the same order around the shape, that we still have named similar shapes. So the most basic ones here are that ABCDE is similar to VWXYZ. They're intentionally set up so that their orientation is the same and it's easier to see those relationships. But in the same way, we could move starting with D and move around the pentagon that way, and we could name that pentagon DCBAE, a totally fine name for the pentagon on the left. In order to name the similar pentagon on the right, though, we would have to start with the point that is corresponding to D, which is Y, and move around the pentagon in the same way and call that YXWVZ. Many different names for similar figures. The one rule, just like congruent figures, is that they have to name the congruent parts, the vertices that make up the congruent angles and the proportional sides in the same relative order. So the first thing I'm going to ask you to do is choose any name that you want for those corresponding pentagons, and then you're going to name the corresponding angles and the corresponding sides. Go ahead, pause the video, copy down these diagrams as well as naming the corresponding angles and corresponding sides. Come back when you're ready to see the answers and move on. So here, as we said before, these pentagons are oriented so that the corresponding vertices and sides are easy to say. As far as the corresponding angles, which we will just call the angles by their vertices, we know that angle A is corresponding to angle V, so they are congruent. Angle B to angle W. Angle C to angle X. Angle D to angle Y, and now I'm just putting the comma between them, and angle E to angle Z, and then I'll go back and make that easier to read. So those are the corresponding angles, and one way that we can talk about corresponding sides is they are the sides that are created by the vertices of corresponding angles. So side AB, created by A and B, is corresponding to the sides that are included between the two corresponding angles, which is VW. And we can continue to walk around the pentagons that way. BC corresponding to WX, DC corresponding to XY, ED corresponding to YZ, and then finally AE corresponding to VZ. So corresponding angles, corresponding sides, we name them and we identify them the same way that we do when we have congruent shapes. Another thing we can do is talk about the ratio that is used to calculate the side lengths of one of the similar figures compared to the other. And that is something that we call the scale factor. It's the ratio of the lengths of two corresponding sides. In similar figures, if all of the side lengths are proportional, the scale factor is the same for each pair of corresponding sides. So go ahead, pause the video, write down the definition of scale factor, and then, as you might imagine, when you come back, you're going to calculate the missing values for x, y, and z. So the first thing we can do with these figures is calculate the scale factor. Now we have z and 10 being corresponding sides, 21 and x, y and 8. None of those are going to allow us to calculate the scale factor, but if we look at the sides at the top of these two trapezoids, what we have is a side of 20 and a side of 30. 20 and 30. That means that the scale factor is the simplified ratio there of 2 to 3. We could have this reversed, and we could have the scale factor be 3 to 2, and that would tell us how to transform from the larger of the two similar shapes to the smaller of the two similar shapes. So now using that, the ratio of all of the different lengths of sides is going to be the same. In this case, because we have 2 to 3, the smaller shape over the larger shape. So to calculate x, the smaller shape has x, and the larger shape has 21. So 2 over 3 is the same as x over 21. We could use cross products here, or we could just recognize that 3 times 7 gives us 21. So 2 times 7 is going to give us x, or x is equal to 14. Go ahead, pause the video, use the same kind of strategy to calculate the values for y and z, keeping an eye on whether or not they are in the smaller of the two similar figures or the larger of the two similar figures. Come back when you're ready to see those answers. Move on to one last idea between similar figures, and then go on to a few practice problems. So here, using the same ratio of 2 to 3 for y is in the larger figure and is relative to 8, so is equal to 8 over y, because the 3 comes from the 30, which is in the larger of the two figures. Again, 2 times 4 is 8, so 3 times 4 is y, which is 12. And then finally, for z and 10, we know that 2 over 3 is equal to 10 over z. Multiply each of them by 5 and get z equals 15. Now you might be saying to yourself now, wait a minute. We just multiplied 2/3 by a bunch of different values to get to x, y, and z. I thought the scale factor for these two similar figures is the same no matter what combination of sides we use. The scale factor here is the same, and 2/3 is the scale factor that we've used. So if we take 20 over 30, which is 2/3, we can now check with the blue sides. Is 8 over 12 that same scale factor? Well, we simplify it by 4, and yes, we find that 2/3 is the same scale factor. So when we're calculating side lengths in similar triangles, similar quadrilaterals, similar figures and polygons generally, we may not always multiply by the same value in our proportions to find the missing value. The key part is that the ratio of corresponding side to corresponding side is the same no matter which pair of corresponding sides we find. So multiplying by 4, multiplying by 5, multiplying by 7, all totally okay, because 20 over 30, 8 over 12, 14 over 21, and 10 over 15 are all 2/3. So what's going to happen next is I'm going to give you 4 figures here. You can determine whether or not they're similar. If they are, you're going to determine what the scale factor is. If they aren't, you're going to say how you know. So here are the 4 figures, A, B, C, and D, and there are 4 different comparisons that you're going to make. A to B, A to C, D to B, and C to D. Are these figures similar, or are they not? Go ahead, pause the video, determine that for yourself, come back when you're ready to see the answers, and move on to 2 remaining practice problems. So for A and B, there are 2 things that we're going to check. Are all the angles the same? Well, A and B both have 4 sets of right angles, so all the angles are congruent to every other angle in those 2 diagrams. Angles, check. Now what about the side lengths? Well, A and B are both rhombuses in addition to both being rectangles, so they are both squares. And the ratio of one side to another, no matter which sides we pick, are going to be 5 in the larger to 2 in the smaller, and that's the same no matter which of the 2 sides we choose between the 2. So side lengths are in proportion. A and B are, in fact, similar. Now, A and C, the angles, those angles check out. A and C both have sets of right angles all through them. But if we look at the ratio between sides, one set of sides from A to C is going to have a ratio of 5 to 4. But then some other sides are going to have a ratio of 5 to 3 because one of the sides of C is not the same as another side of C. That means those ratios are different. Those 2 figures are not similar. Now, if we look at D and B, if we look at the sides are all in proportion. Every side of D is 6 and every side of B is 4. So that means that ratio is going to be 6 to 2 or 3 to 1. That checks out. But take a look at this angle down here in D, where you see it's an 85-degree angle. There are no 85-degree angles in B, which means that the angles do not check out. So those figures are not similar. And for a similar reason between C and D, neither the sides nor the angles fit the criteria. The sides are not proportional and the angles are not congruent because the sides will have ratios of 6 to 4 or 6 to 3, depending on which sides you choose. And with an 85-degree angle in that rhombus, none of those angles in figure D are going to be right angles, unlike the angles in C. So only one of these sets of polygons are similar, that's A and B, and the rest fail for one reason or another. So what you're going to do for these last 2 problems is you're going to find the scale factor in each of the missing values. Once you're done with those 2, that is the end of the video, and we'll do a quick reminder and wrap up of what similar figures are. So first, in these 2 figures here, 2 congruent angles are given. I am telling you that they are similar, so use that information to find the scale factor as well as the missing values for A, B, and C. Pause the video. When you're done with that, we'll go through the answers and get on to the last practice problem. So the one set of corresponding sides that we know are the ratio of 3 to 4. So from smaller to larger polygon, the ratio is 3 to 4. How do we know that those are corresponding sides? Because they fit between the 2 congruent angles that were given as a way of saying which sides are congruent to which. So now we have a bunch of other ratios that we can set up. For A, from smaller to larger, it's the ratio of 9 to A. For B, from smaller to larger, is the ratio of 8 to B. And for C, from smaller to larger, it's the ratio of 6 to C. And now we can just use 3/4 to transform each of those ratios into finding the missing values. So for 3/4 and 9 to A, we can just multiply by 3. So we multiply by 3 for A to get A equals 12. I'm going to skip to C here for a second. From 3 to 6, we just multiply by 2. So from 4 to C, we just multiply by 2 to get that C is equal to 8. And now for 8 to B, it's not quite as simple. So we can use the tricks that we have learned for proportions over the years. 3 over 4 is equal to 8 over B. Use cross products to get 3b is equal to 32, and we can leave this as an improper fraction. It's a totally valid form of a number. 32 over 3 is our value for b. Scale factor 3/4. A is 12, B is 32 over 3, C is 8. One last practice problem here. Go ahead, pause the video, find the missing values X, Y, and Z, find the scale factor between the 2, come back when you are ready to see the answers and do a real quick review. So here we are finding not only angles, or not only side lengths, but also angles. So let's start with the angles. We have 2 right angles, which is true, and we have a 23-degree angle down on the bottom right of this triangle? Well, Z is not corresponding to that 23-degree angle because it is made by the hypotenuse of the right triangle and the smaller side. 23 is made to be included between the hypotenuse of a right triangle and the longer side. So we have to find out what this angle over here is because that corresponds to Z. Well, if one of the angles in a right triangle is 23 degrees, the other, to make it add up to 90 degrees, is going to be 67 degrees. So Z is 67 degrees because these two angles are corresponding and are congruent. Now for the scale factor between the two triangles, we have the smaller leg here and the smaller leg here. Let's do it larger triangle to smaller triangle. That is 15 to 10, which simplifies to 3 to 2 here. So that is the scale factor. And now to calculate y, again, larger to smaller, we have 39 to y. In terms of the hypotenuses, 3 times 13 is 39. So 2 times 13 is y, which is 26. And then finally, we have x and 24. So 3 over 2 is equal to x over 24. X is in the larger of the two figures. 2 times 12 is 24. So 3 times 12 is equal to 36, which is the value for x. So as a quick review, similar figures are ones where their angles are congruent and their corresponding sides are proportional. We can name them in the same way that we name congruent figures. We can calculate their lengths by using what we call a scale factor. The ratio of the lengths of the two corresponding sides in every pair is exactly the same.